This is VLSI data conversion circuits, lecture 15. In the last class we were looking at one of the major non-idealities of a quantizer that you are likely to get when you actually implement one, and that is non-uniform step size. A case in point being a characteristic as shown in black here. The gray line is the ideal staircase type characteristic that you would like to get, but the black one is the one that you actually get. Okay. And we see that if we define for a code K, if we define Vk as the smallest analog input voltage necessary so that the output is code K, then the width of the code is nothing but Vk plus 1 minus Vk. It will have dimensions of volts, right, and we know that nominally this must be one step, one ideal step. So, instead of talking about the actual code width, we might as well talk about the deviation of the actual code width from what it is supposed to be. You understand? So, if this is so that is nothing but Vk plus 1 minus Vk minus one step, okay, and the step size is often denoted by this symbol delta, which is also called the LSB size. Okay. So, in which case this becomes Vk plus 1 minus Vk minus delta. This still has dimensions of volts. So, if we want to talk about a normalized quantity, it makes sense to normalize it to the step size. So, Vk plus 1 minus Vk minus delta divided by delta is what is called the differential nonlinearity of code K, and this is being a normalized quantity will be in terms of the LSBs of the converter. Okay. And this, please note, this is a dimensionless quantity. Is this clear? And it makes sense to call this differential nonlinearity because the local size of the step is basically telling you how steep or not so steep the characteristic is at that in that region, isn't it? I mean, imagine you have a staircase and the height of all the steps is the same, but in some places the steps are narrow, whereas in some places the steps are wide. I mean, clearly you will find it a lot more difficult to climb if the steps are all very narrow, isn't it, and you will find it easy to climb if the steps are all very wide. Okay. So, the width of a step is basically indicating to you how steep the curve is locally, right. In other words, differential nonlinearity is giving you information about the granularity of the characteristic in a certain region, right. You may also, and as we discussed the last time around, if I specified the DNLs for all the codes in the converter, then the characteristic is completely specified, right. You can construct the curve from the DNLs. Another way of putting this information across, where you get also an idea of not just the local variations of the slope, but you get an idea of how globally you are deviating from the ideal staircase. Okay. So, is what is called the integral nonlinearity. I will So, the integral nonlinearity is telling you how far away this transition voltage V k is from the ideal transition, okay, which is the ideal transition corresponding to code k. So, this is V k, this is code k, and this is the ideal transition, but V k is the actual transition, right. So, the ideal transition for code k should be at what input voltage. So, if this is code k, the ideal transition must be at k times delta, but the actual one is V k, all right. So, the difference minus the ideal transition, which is k times delta, is a measure of how much the curve, I mean if you kind of imagine the staircase as some curve which is now not really a straight line because the step sizes are all different, right. This actual transition minus k times delta, which is the ideal transition, is telling you how much that curve deviates from the ideal straight line, you understand. And again the dimensions of this are volts, right, and again it does not make sense to talk about so you basically normalize this to the step size, and again this gives you, this is what is called the integral nonlinearity. Or INL, and this is also clearly a function of the code. So, INL of k. Do you think differential nonlinearity and integral nonlinearity are independent, or pardon? So, I mean both are basically giving you information about the code transitions, right. So, they are not independent of one another, they are just different ways of specifying the same information, right. Okay. So, this for example INL of k is nothing but delta, or rather if I talk about everything normalized to delta, then this is actual transition which is V k minus k delta divided by delta, and INL of k plus 1 is what? V k plus 1 minus k plus 1 delta divided by delta. So, what is INL of k plus 1 minus INL of k? It is simply V k plus 1 minus V k minus delta divided by delta, and this is nothing but the DNL of K, right. I mean, this is not rocket science, okay. You know the INL is giving information about the kth transition, right, and the DNL is nothing but the difference between the k plus 1 I mean the k plus 1th and k transition. So, it makes sense that if you find the successive difference of the INL, you can get the DNL and vice versa. You understand? I mean, these are just, even though DNL and INL consist of this, are basically giving you the same information, they are just two nice ways of giving you an idea of not only the local variations of the characteristic, but also the global picture of the characteristic. Okay. For example, if I find that the DNL, let me ask you a question. So, let us say I plot on the x axis, I plot code, okay, and on the y axis I plot the DNL, and I obviously it will be a sequence, but let us say there are so many codes that when I join all those points it looks like a curve. So, let us say I get a picture like this. What does this mean? Pardon?
If it is symmetric, then it is 0.
Well, okay, so let me call this, okay, let me draw this in a more legible fashion. All right. So, let us say I have a data converter and I plot as a function of code, I plot the DNL normalized to the step size, and at some point here, at some code, I see a big positive jump, and here where let us say this is 1 LSB and this is minus 1 LSB, and here then in the next code it is like this. What does this indicate in the no, what does it say about the, can you make any comment on the shape of the, there is more deviation in the middle, but is there, can you be a little more specific? No?
No, high frequency count. Code is much long.
So, all that this says is that at this code here, right, has a width which is much higher than 1 LSB, and the next code has got a code width which is much smaller than 1 LSB. You understand? So, the characteristic locally around mid code is something which looks, the first code is much wider than, let us say each square here represents the ideal size of the LSB. What this is telling you is that around mid code the characteristic here is much larger than 1 LSB, right, and the next step is much smaller than 1 LSB. So, the code is something like, right, the characteristic is something like this. You understand? if by chance you see somewhere in the DNL plot you see a -1 LSB, you know that that code is missing. What if the DNL becomes more than +1 LSB? Does it mean that there is a missing code? Yes. One code has got, let us say, a DNL of 2 LSB. Does that mean that there is a missing code?
One code will have sitting across twice the LSB.
Yes, so what?
It's not a missing code, but if my VRF was limited, then like.
No. Okay, so let me show you this imaginary scenario. The ideal LSB size is like this. So the ideal staircase is supposed to do this, correct? Now let us say my actual staircase is doing this. You understand? So what is the DNL corresponding to this code? +1, right? And what is happening to this guy? It is not -1, but it is close. Similarly, so is this and so on, right? Because if the DNL exceeds +1 LSB, it does not mean anything, right? You could have, it does not necessarily mean that you have a missing code, because the widths of many other codes could be so small and contribute to this guy getting really wide. You understand? Okay. So it takes a little while getting used to, but once you are used to this jargon, right, and once you do this a few times, looking at the DNL plot, you will be immediately able to guess where potential problem areas are in the converter. You understand? And please note that there is also a very practical reason why you specify DNL. Okay. The other thing to do, if you want to specify the diagram of the characteristic, you would have to specify something which looks like a staircase, and the deviations will be so small compared to the LSB, right. So you will not really be able to make out. Imagine if you have to give this information out, the information about the characteristic as a graph, as a picture, right. Plotting DNL and INL is a very valuable way of doing things, because otherwise it is not possible to give. I can't think of a reasonable way of putting across the information, the same information, in a more efficient manner. You understand? Is this clear? So if you have to draw the characteristic, all that will happen will be that these transitions will be slightly away from the ideal transitions, and if you have a large number of bits, then basically you have to draw a staircase which is this big. You understand? And it will be very difficult to discern changes, and finally you are only interested in the changes. You know what the absolute values, the nominal values are supposed to be, right, and the DNL and the INL plots are giving you exactly that. The DNL is giving you information about local variations in slope, whereas the INL is giving you a broader picture. It is giving you equivalently a bird's eye view of the entire characteristic. Okay. DNL and INL, one may ask, is it important that the DNL is low, or is it important that the INL is low, okay, or are both important, and when are they important? Okay. Well, the answer turns out to be that there are several applications where DNL is very important. Okay. For example, a lot of applications simply cannot tolerate a missing code. Okay. Sometimes you also have what is called a non-monotonic characteristic, alright, where for example this is also a valid staircase. I mean, depending on how you implement it, ideally you are expecting this, okay. But after you implemented it, let us say you got this, okay. I mean, you might argue that this is not supposed to happen, right? Yes, it is not supposed to, but you know, in some converter architectures, if you know bad things happen, this is something that can definitely happen, right. And this is what is called a non-monotonic characteristic. Sometimes there is probably a missing code also, okay. So, in other words, the characteristic kind of does that. Okay. Well, I think I mean see if you will find that the I mean one sufficient condition to make sure that the characteristic is non-monotonic, I mean is not non-monotonic. In other words, if it's the characteristic is monotonic, is to ensure that the absolute value of the DNL does not exceed if mod DNL is less than 1, then all steps exist and all step sizes are between 0 and 2 LSB, right, correct. I mean in the limit, if DNL is plus 1, then you know DNL is minus 1 you have. So, if it is the DNL is less than, absolute value of the DNL is less than 1 LSB, then all steps exist and you will find that this is a definitely a sufficient condition to ensure that the characteristic is monotonic. You understand, okay. And so where do you think a non-monotonic characteristic is likely to be a problem? What applications can you think of where it might be problematic to have a characteristic which is non-monotonic? Very good. Many times an ADC is embedded inside a feedback loop, right. You are measuring something, you want to change something, right, depending on what you measure. So, this is a feedback process and you know as you all know, the loop gain must always be, if you are building a negative feedback system, the sign of the loop gain must always be negative, right. But now if the curve is non-monotonic, then what will happen? You will measure something, right, and let us say what you measure is not what you want and you want that quantity to be increased, you will push, right, but because of the non-monotonicity of the measurement, you will find that you are increasing something, but the actual output is decreasing, and now you know you are totally confused about what to do. You understand, okay, and you will think you are going in the wrong direction and probably change direction. So, whenever A to D converters are embedded inside negative feedback loops, it is a big problem to have a non-monotonic characteristic. You understand? Even if and again depending on application, even if the characteristic is monotonic, there are some applications where the DNL is not very important, whereas the INL is very important. There are some applications where the exact opposite happens, where DNL is very important, but INL is not very important. Okay. The classic examples I would like to give for these situations are DNL is important while INL is not. For example, displace. Okay. Right. Yeah. So, the same definitions will also hold for a digital to analog converter, where you put in the input and the output is analog, right. But for example, you have a picture, right, and in the olden days, before everything was completely digital, it turns out that even parts of the signal chain were you have to convert from analog to digital to be able to take the analog and then make it interface with the digital TV, for example, right, in which case you will have to convert the analog waveform into a digital one and then interface that to a digital display. Okay. So, there was a time maybe about 10 years ago where this transition was happening. Displays were all analog, and then then we start getting LCD TVs and so on, and then there needed to be some glue electronics to be able to take the analog signal and then generate some digital word corresponding to color and so on. So, in these imaging applications, it is very important to have good DNL. Why? Because see, in most images, right, a lot of patches of color occur in one place. You understand? It is not as if very often you have color transitioning from black to white. It does not happen in one pixel. You understand? So, in other words, when you scan the beam over definite regions or significant regions, the code will only change slightly, right. Now, the eye is very good at picking up contrast, local contrast. So, if the LSB size is varying, right, a lot across neighboring inputs, right, when the input is very close, that is when the pixel is supposed to be will also be close, is not it. When the two inputs are very close, the two analog inputs are very close, but the step size is way different, then it will show up as a difference in intensity finally somewhere, right, because you are using this digital information to do something else. And it turns out that the eye is very good at catching edges and contrast. Okay. So, whereas if this varied slowly from the left side to the right side, okay, given that the picture itself is has whole bunch of randomness in it, you will not immediately discern that it is not be irritating to the eye. Okay. While if you put a constant color pattern, like if you put a blue pattern or something, you will be easily able to see that the blue here intensity and that is not the same. But when you are playing a movie or something like that, where the images are changing, you will not be able to discern it. Whereas if you suddenly see neighboring pixels where the intensity is very different, then experience tells us that it is very easy to catch, right. And applications where INL is important while DNL is not as important, is communication systems, especially wireless systems where you are trying to receive many channels, and if there is a gentle nonlinearity, it turns out that channels which you are not supposed to receive, right, or you are not interested in, strong channels can actually fold back onto the desired channel and basically cause interference. I will not get into the details, but I will just mention it here. What I want to say is that whether DNL is important or INL is important is a very application specific thing, but one thing is for sure, you typically do not want converters which are non-monotonic. Okay. Of course, in a negative feedback loop that would be a complete disaster, but even otherwise in general you would not want non-monotonic converters. Okay. If and as an illustration, I will just give you, if the ideal characteristic kind of looks like this, right, where I am saying that there are so many codes that the steps are not visible, and the actual characteristic is like this, all right, the INL will be what is the INL? This is the analog input, this is the digital code, right. So, which is the INL here? This is the INL. So, if I plot the INL as a function of k, it will be 0 here and 0 at the end, and it will peak somewhere in the middle, right. So, it will be, the INL will look something like this, right. This is code, this is INL. You understand? Okay. Yes.
For this non-monotonic, how will you define DNL alone? Because for some codes there may be two different vehicles.
Yeah. So, I mean, one second. Yeah. So, oftentimes you will find that when the stuff is non-monotonic, then different codes will have, when you are trying to do this transition test, you will find that you will have errors in the test because you do not know, there are different ranges for which you get the same code. So, that will be a pathological condition, you will be able to figure that out very easily, right. So, usually therefore, it is often you want to make sure that the DNL is always less than, if the DNL is less than 1 LSB, the magnitude of the DNL is less than 1 LSB, then you are absolutely sure that the characteristic is monotonic. Okay. All right. So, going forward, in reality of course, you will get all these problems together, right. It is not as if you will have only offset or only gain error or only step size mismatch. The ideal characteristic is something like this and the actual one is probably something like this. Now, the question is, if you measure an A to D converter and it has this characteristic, how will you extract its, you would want to specify to a customer what the, we want to tell him what V offset, him or her what V offset is, what gain error he can expect, the DNL and the IN, correct. So, any suggestions on what I should do? Clearly, this is my ideal staircase. One way of doing it is to say this is my ideal transition, this is my the actual one. So, this is my INL, right. Similarly, the INL here is this much and so on. So, do you think that makes sense? Is that a good way to do it? I mean, okay. So, let me, so let us say our converter simply had a gain error, right, which as we saw is a benign thing. Now, if you simply define the INL as the deviation between the transitions for the ideal case versus the actual case, even though this converter is a pretty good one, you will see that the INL can become very, very large, you understand, okay, simply because the slopes are different, you understand. And I mean, finally you are trying to sell as many parts as possible by claiming that your part is a very good part. So, you know, this is definitely not a good sales idea, right. So, you should come up with a, within quotes, smarter way of defining things, where all your numbers look good, you understand, okay, because you know that in many applications anyway the absolute accuracy, you know, if there is a gain error, it does not really matter, they will fix it in the system. If there is a small offset, it does not matter, they will fix it in the system, right. So, then when what do you think is a better way of defining INL? And
no, instead of using that delta value, they can find out the average value of the bits.
okay,
That will get rid of to some extent the gain error.
okay. So, that is a good suggestion, right. So, what he is saying is that, okay, I know that this is my code transition corresponding to in this case 7, right. So, V7, and this is the code transition corresponding to V1, okay. I mean, all these normalized INLs only depend on, or DNLs for example, only depend on the step size, correct. So, clearly because of gain error, my step size is not the same as the ideal step size that I wanted in the first place, correct. So, the what I would like to do is to try and figure out what my actual step size is, and given V7 and V1, it is very straightforward to figure out the step size, because I know I must have 6 steps within this range, right. I know V7 and V1. So, V7 minus V1 by 6 is a good, is a much better approximation to the LSB rather than use the ideal LSB I was trying to realize, you understand. Is that clear? Okay. Okay, you understand. And even better way of doing this is to say, I will calculate my LSB after removing, I mean, this is one way of removing the so called gain error. Gain error is nothing but LSB size not being what you wanted it to be, correct. So, removing gain error means that I will make what I wanted it to be equal to what it actually is, but unfortunately the LSB is not, I mean, the step sizes are not uniform. So, you need to come up with some kind of average step size. One way of doing that is to say, I will find the last point, the first point, I know so many codes are there. So, one way of measuring the average step size is to find the range divided by the number of codes, correct, alright, and that will give me my the actual LSB size that I have with my converter, and if I use that, my INL numbers, my for example, definitely my DNL numbers all start to look much better than what they, I mean, what I would have got if I had used the ideal LSB size. Does it make sense? Okay. And but this still does not solve the problem of offset. if I had offset and even if my staircase was perfect, right, the ideal transition point is here, the actual transition point is here. So, if I find the INL, it is a constant INL, but this is a large number of LSBs potentially, correct. But otherwise my staircase is actually quite nice, uniform step size, gain of 1, you understand. So, it is not just enough to remove the gain error, you must also remove, if you remove offset. So, to find DNL and INL from measurements, for example, the first step is to remove gain and offset errors. Okay. And how do you remove gain and offset errors? What do you think? I mean, there are many ways of doing this. Can you suggest something?
No, find the average LFP size.
Okay.
And then find out the difference between that and the first transition.
Okay.
That will give you the offset.
Okay.
So you subtract that offset.
Okay. So that is one way of doing it, alright. Another way of doing it is to say if the staircase was ideal, then if I joined all these points, I mean this is a more within quotes somewhat more rigorous way of doing things, right. The basic ideas are very much the same. You need to get rid of offset error, gain error. If I join the midpoints of all these codes, what should I get? I should get a perfect straight line with this offset being equal to delta by 2, correct. Now, I am going to do the same for my actual measured characteristic. I am not going to get a straight line, right. This, if I join all these points, I will probably get something like that. Okay. All right. Now, I am going to say let me try and find the best fit straight line which approximates this curve, let us say in the least square sense. Okay. So, I will find a best fit straight line which probably does, this is clearly not best fit, but let us say this is a straight line, the one in blue, and this is the best fit straight line. Okay. So, clearly from the slope of the best fit straight line, I will be able to get my true LSB size, correct. Ideally, if the code, if the y goes up by 1, the x must change by delta, right. Now, I have a line whose slope is not quite what it is supposed to be if the step size was ideal, but once I do the fit, I will be able to extract the slope and from that the size of the step. That takes care of gain error. And we know that this straight line must intersect the y axis at step size by 2, right. Okay. But it actually is not intersecting it at step size by 2. The difference between the two must therefore be the offset. Okay. So, once you know this, you can offset, you can generate within quotes the ideal staircase, right. I mean you can add offset and gain error to the ideal staircase to get something with a uniform step size, but without gain and offset errors, right. In other words, you will probably get a modified something like this, where the step sizes are all the same. The ideal staircase now has an offset and a gain error which is exactly the same as the average gain of. Does this make sense at all? No? Okay. So, we know that this slope is not the same as this slope, correct? You people understand how I got the other slope? I just fit a straight line, okay. That slope is not the same as the ideal slope. So, if I want, I mean my problem is that this ideal staircase is not a good reference to subtract from, that is the problem, and that is because I have benign offset and gain error. So, if I add offset to the ideal, if I moved, in other words, if I moved the ideal over just by the right amount, and if I change the slope of the ideal staircase by the right amount, then my ideal staircase would probably look like something like this, you understand. So, the deviations from here should give me an INL which is a more realistic estimate of what is really happening with the converter, you understand. Because we know that if you simply shift the curve and if you subtract from the ideal characteristic, you will get a large INL, but that is not really bad because INL is constant for all codes. Similarly, if there was simply a gain error and there was nothing else wrong with the converter, if I subtracted the actual transitions from the ideal transitions, okay, the INL would simply keep increasing as I increase the code. And again, this is not really a bad converter, it is just that there is a gain error. So, what we need to do to get a true idea of the nonlinearity is to remove offset and gain error, and one common way of doing it is to find a best fit straight line to the staircase that you actually measure, and from there go and calculate the true gain and the true offset, and you can either subtract that from the actual measured values or you add this offset error and gain error to the ideal staircase and you subtract the measured ones from the ideal one which has been corrupted by offset and gain, which is exactly the same as what your converter has. So, in other words, the ideal and the actual one will straddle each other and not be so far away, you understand. So, fitting is a nice way of simply making sure that you compare two things which are sufficiently close. Does it make sense? Okay. The next thing that we need to, so this covers what is called the static part of the quantizer characteristic. We need to figure out what happens when you excite the quantizer with a sinusoid and look at its spectrum. I mean, clearly quantization involves loss of information because many inputs are potentially translating to the same output, which means that you have lost information, correct. So, we will talk about the spectral properties of quantized signals in the next class.